don't have the same knowledge representation. You don't have the same actions. Most of all, you just don't have the same problem. And they're all domain-specific engineering, or if we might say it a bit more candidly, hacks. So the state of the art, like in Torx car racing, we have hand-coded heuristics optimized with evolution, but a little bit. I think Cobostar is the current best controller. It has a little bit of learning of the track. Basically, it's the first time it drives a lap on a track, or the first lap on a track, it learns to figure out where the sort of tricky parts are and remembers it and lowers the speed again. But it has very little of what we call AI, except the sort of offline optimization with evolutionary computation. Interesting enough, and this is a pattern we see more and more, or we've seen over and over again. It's like the first time you run this kind of competition such as this, like naive and ambitious people submit their best general AI solutions to the problem and don't do particularly well. And then you run the competition a few more times, and people come up with these sort of very clever hand-designed things, with hand-designed sort of solutions where they put the best sort of domain-specific strategies into the code and perform much better. So it's a domain knowledge versus AI. Basically, AI goes out and domain knowledge goes in. Go, we have deep learning plus MCTS, which is a fairly general. I mean, we're talking about DeepMind's AlphaGo now. Deep learning plus MCTS combined in an interestingly clever way is a fairly general solution. However, and they say this would essentially work for any perfect information game. I'm not so convinced of that, because basically, my take on it is that if you wanted to design a game which a convolutional network would be able to play well, you would design Go. It has exactly the right properties for this, with all sort of local structure, and which is the same all over, plus the global structure. So the important thing is, like, AlphaGo was trained for like months of training time in order to be able to play again Lee Sedol. Even if the same architecture could play another game, you would have months of training time again to sort of teach it that. So that's not particularly general intelligence, I would say. And StarCraft, which is probably almost certainly the hardest of any of the games we talked about so far. StarCraft is way harder than Go. The reigning champion is a horrible clutch of if-then statements. It's terrible. It's a disgrace. It's a shame for AI research.
That's a bold statement.
Yeah. No, but I think it's called Overlord, or Overmind, or something. And it's made by someone who is not an academic, is just a very good StarCraft player, and he encodes all his best strategies into the code. And that's what happens. And it wins against all the clever AI solutions. Okay, so we have an issue. What are we going to do about this? Using individual games as AI benchmarks. And by the way, what I'm saying here is true for board games as well. Deep Blue, brilliant engineering, but basically a lot of like domain-specific sort of heuristics put into this.
Design games that actually require intelligence?
Yeah, that would be good. But these are the games that are best designed for humans. So my take on it, basically, I never show questions and slides, and if I do, I show one, and it would usually be this one. This is, I guess most of you are familiar with this. This is Shane Legg and Marcus Huckler's formulation of general intelligence. And Shane is not here, right? No. Marcus is not here, no. Basically, their idea is that your general intelligence is the sum of the performance of an agent on all possible problems weighted by the simplicity. So basically here, general intelligence of pi being a policy or an agent, is the sum over all environments of v here of pi over mu is like the reward that agent gets under that environment, or we can say game in this case, weighted by 2 to the power of minus the Kolmogorov complexity of the environment. So basically, the weight is so that the more fundamental problems that can be described in a shorter, with a shorter description are weighted more heavily. Which is a way of trying to get around the no free lunch problem. You can argue about whether it succeeds or not, but basically, it's a fairly good intuition. I mean, sort of more obvious, simpler tasks should be more important than the more obscure ones. Of course, this equation is entirely impossible to measure in any way because, first of all, you need to measure over, you need to average, over all possible problems in the world, which is a bit hard, takes some time. And also Kolmogorov complexity is uncomputable. So it's sort of twice impossible to sort of come up with a good measure here. But I think the intuition behind this formulation is pretty brilliant. We need to look at performance over a number of problems and perhaps weight them depending on how important they are. So can we do that? Can we construct an AI that can play many games? You know, if we had something that could play anything we threw at it, it would be pretty general intelligent. You know, we don't train it for StarCraft or Super Mario Bros. Or car racing, and then we just give it a game and it performs well. That would be brilliant, right? Yeah.
Could you at least maybe add the constraint that it can read the construction or the instruction manual or something like that? You know, or like maybe.
I mean, it's like I could answer this one of these snarks, but I'm not a very snarky person. But you know, back in the 80s, games actually came with instruction manuals. These days, you just start playing, and it has a nice on-screen tutorial that gives you things. Yeah, I mean, in a more general way, your question makes sense because basically, how much? I mean, would you want to test your ability to solve a problem, play a game immediately? Or would you want to test it after some training time? And I'm going to show you some examples of both. We've gone so far in what I've been doing for like no training time. It's like your immediate performance. Maybe we should change that. Maybe we should give them some sort of time to sort of train and sort of learn and so on. I also don't believe in giving it like months of computation time. Because then you're suddenly not testing your general intelligence, then you're testing something else.
People have to study Go to play decent Go. It takes a while.
Yeah, but if you test your general intelligence, wouldn't it be more relevant to test your general intelligence on how fast you can pick up Go and how well you can play it after like playing it for an hour or a day or something like this?
Yeah.
I mean, anyone can put in 10,000 hours of reflective practice or something like this.
I mean, there's 9x9 capture Go for little kids.
I think for Go, it's a little bit between those two extremes. Because an hour of Go, for me, I was too idiotic to learn much. But if you play like 100 games of Go as a human, if you're paying attention, you'll become an advanced beginner, or at least an intermediate beginner, right?
Yeah.
And so you are abstracting something to do that.
Yeah, so what Ben is saying here is like 100 hours of Go is like your performance on that. After 100 hours of Go would probably reflect your general intelligence very well.
Go or StarCraft are too hard for an hour to how much I would think.
Yeah, I don't know. I mean, at the same time, I mean.
Maybe I'm just dumb at
Yeah,
playing games.
I mean, someone should do this. Someone should do like some kind of comprehensive intelligence test of people, and then basically give them Go, StarCraft, and Legend of Zelda or something like this, and a couple of different things, and ask them to play it and see how much it correlates. I mean, does it correlate best to your instantaneous performance in a new game, or your performance after 10 minutes, or an hour, or 10, or 100 hours?
Well, it's a gift, though. Like some people are gifted at picking up new video games, which is loosely correlated, but not uncorrelated with other forms of intelligence.
Yeah. Yeah, so just repeating, some people are gifted at picking up new video games. It's correlated, but how correlated with intelligence? So I'm going to go through 3 examples here. Also, someone should keep track of my time, how much I'm talking, and tell me to shut up. shut up, you know, at some point when I should shut up.
I'm listening, watching the clock. You got loads of time.
Oh, brilliant.
Ramble on.
So here's 3 examples of what I consider the main frameworks or benchmarks for testing your performance not on one game, but on many of them. So we're going to go through a general game playing competition, the arcade learning environment, and general video game AI, and what's been done there. Obviously, I'm biased as I'm one of the people who organize the general video game AI competition, so I'll talk most about that. It's my prerogative. Starting with, and let's have a look at what requirements we could ask on these games first. So I think requirements are like, yes, there should be good games for humans to play. We could easily invent any number of crap games and test the performance on those. But how relevant would that be? I mean, for example, I haven't done this, but I think you could easily automatically generate games that computers could play, but humans would be completely chanceless at. Here's a game with 5 million states connected in completely incomprehensible ways, and you have 100,000 actions to do to try, and it's hopeless. You have no way of even developing any kind of intuition what's happening. A computer could do basically a one-step look-ahead search and win over you every time, which does not mean that one step. And then you could develop 1 million variations of these games with different state tables, and one step look ahead would win over you every time. That doesn't mean that one step look ahead is more intelligent than you are. At least that goes for most of you, I hope. But basically, it just means that the benchmark is perhaps irrelevant. So we need to have good games that are good for humans to play to keep the benchmark relevant. We need to challenge a broad range of cognitive skills. And here's the issue with straight board games, is that they are fairly narrow. It's essentially all reasoning and planning, whereas games actually can challenge much more than that. Perception, reaction, coordination, all kinds of timing and so on. And importantly, it should not be one game. It should be a number of different games. So basically, agents should be testing games that are unseen by the developers. So basically, if you're developing an agent, you can absolutely not know what games you're being tested on. Right, so start with a general game playing competition. They made this very nice picture, I like it a lot. This is basically, and which pretty much illustrates what's happening over here. We're talking about classic board games and classic board game-like games, mostly with discrete movement, turn-based games, perfect information, even though that's not completely necessary. Most of the games have perfect information, even though you can have non-perfect information these days. They have lots of restrictions in various ways on what games you can have, but these are the type of games. So basically, they're described in what's a game description language, which is simply called game description language, which is a Prolog-like variant of Datalog. So it's essentially first order logic, which makes these descriptions extremely verbose. So tic-tac-toe, it can be defined in a 3 pages of text in this language. Agents are given the full description of the game. So basically, when you submit an agent in this competition, it's given a full description of the game and some time, I'm not sure exactly how much time, an hour or so, to basically crunch this description, reason about it, come up with his own best sort of way of playing this game, and then playing the game. Usually, playing is done with Monte Carlo research. Anyone here never heard of Monte Carlo research? Just struck me that might not be a... Yes, good. Monte Carlo research is a beautiful algorithm that came out of research on Go around 10 years ago. It's a statistical research algorithm, so it's a bit like Minimax, where you sort of look ahead at what kind of actions you can take and what kind of actions the opponent can take if it's an adversarial game, or otherwise just what sort of actions you can take in the future. But you don't necessarily need to have an evaluation function that tells you how good a state is. You can estimate that by rolling out until the end. So basically doing random actions and see whether you win or lose the game in the end, which is so simple and so nice. And then it basically builds these unbalanced trees. Because it acts as the best first algorithm and goes down the routes which are most promising, most interesting right now when it builds a search tree. It's you're gonna hear more about it because this is the algorithm that essentially makes general game playing possible at all. So much of the progress in this competition is really about reasoning about the games. And every time this competition is run, they make a handful of new games, but largely because it is very, very hard to make these games in this very verbose language, they tend to be fairly simple games and variations of other games that existed before. Moving on, the next thing is the arcade learning environment. So this is what you see here are screenshots from this arcade learning environments, and they don't look so hot by today's standards because it's based on an emulation of a machine from 1977. These games here, we have Breakout, and then we have, I think, Freeway, and a version of Pac-Man, not the best version of Pac-Man, and Defender maybe? Not entirely sure. So basically, it's based on an emulation of the Atari 2600. Atari 2600 is a very fast machine to emulate. It had, I think, a 1 megahertz 6502 processor. It had 128 bytes of memories. There's no kilobytes or megabyte or gigabyte in that is 128 bytes of memory. There's no screen buffer. Programming a game for this includes keeping track of where the electron beam on the TV is at where the scan line in this case at any particular time, so that you can update, you can change around what amounts to screen memory before that part of the screen is updated. It is probably one of the hardest platforms to develop anything forever. Most games had to fit into like 2 kilobytes of ROM, which was on a cartridge. It had no system timer, so you could not really do a random number generator in any simple way, which means that most games are completely deterministic. Still, it was extremely successful. It has a game library of like 400 or 500 games or something like this in total, including lots of the classics. I mean, you have Breakout version of Pac-Man, some version of Defender. You even have some very, very simple platform games. You have the classical adventure, which is like the precursor to all sort of graphical adventure games like Zelda and so on. Some of the games are actually good, but it is a very, very simple machine. So in this A&E framework, you have this emulator, and then it basically runs the games for you. You get the screenshot, raw pixels, 256 by 128 pixels or something like this, I think. And then your agent is fed the raw screen data and needs to reason over this and return the joystick commands used to play the game, which is a pretty interesting task. So there's a lot of perception involved. Most successful agents are based on deep learning. This is by far and away the most famous of these benchmarks because it was used in DeepMind's Nature paper from last year, where they showed that they could train deep neural nets with Q-learning to play these games. And this, I don't know if this is not readable from back there, sorry, this is a figure from the actual paper, which basically shows how well it performed on each of these games. And the dividing line there is, the horizontal line there is at human level or above or below human level. So we can look at here, basically, video pinball, boxing, Breakout, Robotank, Crazy Climber, and so on, are way above human level in game playing skill. Whereas things such as Chopper Command, Centipede, Saxon, Alien, Sequest, Miss Pac-Man are much below human level. But interesting enough, it actually managed to play the majority of games available in this benchmark at the time at human level or above. Which is, there's a reason this got into Nature. This is very impressive research. Very, very impressive results they got here. However, Is it general intelligence? So basically, looking at how much you train these games and these networks, you train them for about 38 days of gameplay per, so more than a month of gameplay time per game. So if you play the same game for like 8 hours a day for 3 months, you'd probably be good at it. So a network trained for a particular game cannot play any other game. So there's no transfer learning. There's some papers that come out afterwards. I haven't looked much deeper into it, with some results on transfer learning from one game to another, but not very strong results. So basically, it's not like they train a big deep neural network and can suddenly play all these games. You can train it and can play Breakout, but not Pac-Man and not anything else. Yes?
Okay, I understand that these are games played by humans and manually, where speed matters, not like
Yeah.
chess that you can just say what a move is, but speed matters. So how you compare this if this human factor is taken into account? Because
It is, basically it is, in practice, sure, you have an advantage by having superhuman, reactions and so on, but in practice your advantage is not that big because they're all designed, and this goes back to the original idea. We need to work in games that are good for humans, for it to be meaningful. These games are designed to be beatable by humans. So basically, you have an advantage by having superhuman reactions, but not that big an advantage. The worst sort of, in a game such as Counter-Strike or Unreal Tournament and first-person shooter, you do have a huge advantage, and that's a problem. But in most games, it's manageable. And in games where humans still perform much better than AI, which is like all of those at the bottom here. Basically what happens is that these deep neural networks can't plan ahead, far ahead enough, and humans win on being able to plan ahead. Yeah?
So I guess my specific question for like first-person shooters would be if you trained it on one first-person shooter and then apply a different first-person shooter, how would that, because of the intricate, like the small differences in the...
Yeah, well, good question. Someone should set up a benchmark where it's possible to play a number of first-person shooters. The problem with doing this kind of research is that you need to actually get hold of the code, and you need to integrate in the same framework, and you need to have it run fast enough. I haven't seen anyone do this. I've only seen people work on particular shooters. Some old ID software games are open source, including original Quake and original Doom, and you could probably put this together for a benchmark where you can play any of these. Something to do. So anyway, so basically